All right. In this module, we're going to go over an example problem of these isothermal transformations that we learned about in the last module. Okay, so what I want you to do in this module, and you can fill it out here in your own notebook, or if there's a quiz, fill it out there. But what I want you to do is using the uh, isothermal transformation diagram provided. So this is the one for the eutectoid composition. I want you to sketch and label the time temperature paths on the isothermal transformation diagram provided here for 3 different microstructures. So basically, what is the pathway to get 100% coarse pearlite, and then another pathway to get 50% martensite, 50% austenite, and then how could we get 50% coarse pearlite, 25% bainite, and 25% martensite. So see if you can sketch those out and then come back after you've done that, and we're going to go through this one together. All right, so we're back, and I want to go over this question with you. So we're going to sketch and label these time temperature pathways to get the following microstructures. So the best way for me to do this is on top of an isothermal transformation diagram. So I'm going to keep on the slides, but I'm going to augment them with the pen. So the first thing that it wants us to do is 100%, let's just go back here for a second, 100% coarse pearlite. Okay, so first of all, we're looking at this time temperature transformation or isothermal transformation diagram. The A represents austenite, M martensite, P pearlite, B bainite. So if we're looking for pearlite, it's going to be in this region above roughly 550. And if we want to go back here, so we have to do it above 550. But the next thing, the other thing we have to consider is the term coarse. And if you'll recall from a few modules ago, the coarse was a function of temperature. And the higher the temperature, the more coarse something is, because the layers of pearlite are thicker, and therefore, because at the higher temperatures, the diffusion times are faster, we can have coarser or thicker layers. So coarse is going to be at the higher end of the range. So if our range is from 550 up to 727, right, we're going to pick somewhere in the high end of that. Okay, so let's go over how we would draw this. And again, like I said, I'm going to use the pen. And so we're going to start above the eutectoid temperature, right? So let's say we pick 800 degrees. That's our starting point. So when we have this isothermal transformation diagram, it implies that we're doing this at one temperature. So when we go from 800, we're going to go from 800 to whatever our temperature is very rapidly. So basically almost instantaneously, so that it is still isothermal. We don't want to cool down slowly from 800 to another temperature, because then that would no longer be isothermal, right? Same temperature. So we're going to pick a temperature up here in the top range that would have coarse pearlite. So we can do it about 675, like we talked about before. So we're going to basically cool almost instantaneously to 675. It could be a slightly different temperature. It doesn't have to be that exact one. But the first step of this is that we're going to pretty rapidly, so just almost a vertical line to that temperature. And then, as part of our isothermal treatment, we're going to hold at that temperature and go horizontally across. So I'm doing this with the pen, so it might not be perfect, but imagine this is a line, a straight line, right? And so this is the first part. So this is I'm going to call this A. So this is 100% coarse pearlite. So we basically, the way you'd follow this is we are above the eutectoid temperature at 800. We rapidly cool to 675 or a close temperature to that. And we hold until we have complete transformation, which, if you remember correctly, that green curve is where we have the 100% transformation of austenite to pearlite, right? So that, if you follow it down, is close to 10 to the third seconds. So the reaction starts a little past 10 seconds and then goes to about 10 to the third. So again, it does take some amount of time from when we start over here. All right, so that is the first one. So this is A. All right, and then I'm gonna switch colors here. Hopefully, there we go. Let's do blue. And look at the second one now. So 50% Martensite, 50% austenite. Okay, so austenite is A, M is Martensite. So basically we're saying we want 50% Martensite, 50% austenite. And you'll notice that down here it literally says Martensite or M 50%, right? So that's where we're going to have 50% Martensite. So if we take our previous 800 and we rapidly quench and cool to this temperature, right? So this is, somewhere maybe 160, 170, somewhere right here, right? So let's call that 175. So if we cool to that temperature, that's going to transform 50% of the initial austenite to Martensite. So at that temperature and at that temperature only, will we have a mixture of 50% Martensite and 50% austenite. So here's the kind of trick to this one. If we, like most of these, so for example, let me go back real quickly and switch colors and consider the first path. So after this time right here, where we've reached the green curve, this is 100% coarse pearlite. If I quench it now, so if I decrease the temperature rapidly and go down here, I don't form Martensite because Martensite transforms from austenite. So if I've already formed pearlite, I cannot form Martensite. So it's okay to quench after you've transformed into pearlite or after you've transformed into bainite. Here, on the other hand, let's switch back and consider this second one. On this hand, if I do, in this case, if I have 50% austenite and 50% Martensite, if I continue to cool down, you'll transform the rest of that austenite into Martensite. So the only way I can maintain 50% Martensite and 50% austenite is to hold at this temperature indefinitely. And so I'll just kind of put an arrow, right? So that's the only way I'm going to get that. So that's the kind of trick compared to this one, right? So if I do any sort of other temperature decreases, that will give me Martensite, more Martensite. So the only way I can maintain that austenite is if I hold indefinitely at this temperature of approximately 175. All right, so that one's kind of, that's the trick to that one. So let's go back and look at the last one. So I'll switch colors again, and let's do green. So this is going to be C. All right, so 50% coarse pearlite, 50% coarse pearlite, 25% bainite, and 25% martensite. So you can see this one might be a little trickier because we've got multiple components here. All right, but the first part is coarse pearlite. So we're going to start at the same temperature, and we're actually going to follow the same path, and I'll just do it slightly differently. Excuse me. And then we're going to follow the same path up to a point of coarse pearlite, right? The same temperature. However, this dashed line right here is the 50%, right? It says 50% here. So we only have to hold until that time. And so at that time, we have 50% coarse pearlite, and the rest is still austenite. So nothing's transformed about that. So that's how we're going to start. Then, if we want to get the other two components of bainite and martensite, we are going to have to do different temperatures. We are going to have to transfer again or cool again. And so the next thing that we wanted to get was we wanted to get 25% bainite. So what I'm going to have to do is I'm going to have to go to the bainite region, which is below 550 and above the martensite start, so anywhere in this region. So I'm going to rapidly cool to, let's say, 450. And then here's where it starts to look a little tricky. So once we've cooled to a lower temperature, the process starts over. So we actually need to kind of go back in time effectively, kind of have to go back like this. Go back to the start at 0. Because once we're at a new isothermal temperature, we start over in time. So from there, then we start the process over again, and we would go until we form bainite, right? So this is where we start to form bainite. But we only wanted 25%, right? So half of the remaining austenite. And so we're going to go to this point, right? So we form 50% bainite from the remaining 50% austenite, and so that's 25%, right? So we go to that point. And then the remainder, we want to be martensite. So the 25, the last, if we go back real quick, the last 25, the remaining austenite should go to martensite. And so that's where we're going to basically rapidly quench. So if we rapidly quench, the remaining austenite that's left over will become martensite. So that's kind of a multi-step process, obviously, where you do an initial isothermal transformation to get 50% coarse pearlite, and then we want to rapidly quench to a temperature in the bainite region. That reaction starts over again, but we only want 50%, so we only go to this 50% line, and that will give us 50% of 50, which is 25, and then the remaining 25% austenite is done by quenching, right? So this is C. So that one's a little bit complex because we have the multiple components there. So that's how we get each of these microstructures here from isothermal transformation diagram of this eutectoid steel.